AP Chemistry, let's keep going in Chapter 1. Now we're talking about organization of matter. We are on Chapter 1, Section 9, so 1.9. We're going to finish out the chapter. Oh, goodness. Too fast. So we have matter. Okay, matter is best defined as anything occupying space or having mass. It's the material of the universe. Matter is complex and has many levels of organization. And in this this video lecture, we're going to look at that. Now, over here we have mixtures. Okay, most of matter around us consists of mixtures of different pure substances: wood, gas, soil, air. They're all mixtures. The main characteristic of a mixture is that it has variable composition. Okay? For example, wood is a mixture of substances and the proportions of which vary depending on what type of wood and where it grows. So obviously the type of wood that grows in a pine tree is going to be different than the type of wood that grows in an oak tree. Obviously. Now, of mixtures, we have two main kinds. We have homogeneous, okay? Homo meaning same. Genus coming from the same type of word of like genre or genus. Means type, okay, general type. So same type. So homogeneous, you can think of it as having visibly indistinguishable parts. Okay, it's all the same. Whereas heterogeneous, hetero coming from different, genus again coming from a type, different types, having visibly distinguishable parts. There's different stuff in here. Now, going back to the homogeneous mixture, there's also called solutions. Okay, solutions. We're going to be using solutions in this class during different wet labs, talking about solutions and calculations. But it's not just the liquids that we are going to be using in class that are solutions. Air, the stuff that you're breathing right now, is a solution. It consists of a mixture of gases that you can't distinguish between right now. The soda that you drink or the energy drink that you drink is a complex liquid solution. That's liquid. Brass, okay, a solid metal, is a solution of copper and zinc. It's mixed together. And so you can have solutions in all these different phases of matter. Now, if we just talk about pure substances, there are different types of pure substances that we can talk about. And by the way, a pure substance, when I say pure substance, I don't just mean a pure element. That while it is a pure substance, I can have a pure substance that is made of more than one element. For example, water. Water is a pure substance, but it's made up of two different elements, hydrogen and oxygen. Okay, so I can have a pure substance that is a combination of different elements. As long as it is only H2O, purely it is considered a pure substance. Now, elements, things like hydrogen, oxygen, nitrogen, fluorine, those are going to be broken down into atoms. Okay, so elements are made up of atoms. Atoms have two main regions. One region is the electron. We will be looking at electrons quite a bit during this course, especially as we get a few more chapters into the book. We'll be talking about the quantum mechanical model of the electron, also known as the electron cloud. We'll be using that term as well. And then the nucleus, where all the protons and neutrons are located, the source of the positive charge. Most of the mass of the atom is found in the nucleus. Now, the nucleus is made up, like I said, made up of protons and neutrons. There was a time way back in the day with Democritus and John Dalton. These guys thought that the atom, the reason it's called an atom is it comes from the Greek word atomos, which means the uncuttable or undivisible. They thought this was the smallest bit of matter that existed. And so they called it the atom, the atomos, the uncuttable. But as time wore on and as science developed and different types of experimentation, different instruments were developed, it was found that there actually are smaller things than atoms. For example, electrons, protons, and neutrons. Well, after more time has passed and instrumentation has improved even more, it's now found that there are things even smaller than neutrons and protons and electrons. They're called quarks. And then there are things even smaller than that now that are way beyond the scope of my schooling, things like bosons and very, very difficult things to imagine because of how small they are and how they behave. We are going to move into the phase differences. We're actually going to spend a lot of time on this in a future chapter, but for now, we want to make sure that we understand that there are three main states of matter that we will be dealing with. There is a fourth, and it's actually the most common in our universe, called plasma. But we're going to be dealing with things like solids. It's something that has a definite volume and shape, and particles are packed into fixed positions. You can see up in here in this grid, these are locked in place. They do not move. They cannot move relative to one another. So it has a definite volume and a different shape, because these things will not move. They won't expand, they won't contract, and they won't move around to change shape. You have the liquid. It has definite volume. Okay, this many of these particles isn't going to change how much space they take up, but they have indefinite shape. Okay, they have definition. They're going to move around relative to one another and change the shape. Particles close together, but they are not in fixed position. So this individual molecule right here can move around. It can end up down here, but it's not going to simply merge with this molecule. It'll just displace this molecule, and it will move up, and it will further displace. And so the volume will not change, but the shape will. Then we have gas. Gas neither has a definite volume nor definite shape. These particles are actually at huge distances from one another, and I'll try to describe how much of a distance they are from one another when we get to that chapter. But because they are these huge distances, they have no attraction or repulsion to one another, at least in that ideal gas idea. And so they're the huge distances. They definitely don't have a definite shape, and that is gas. Last is a plasma. It's at very, very high temperatures, a completely ionized phase of matter. And the reason it's the most common thing found in the universe because it's what stars are made up of. That's the state of matter that star stuff is, and that's 99.8% of our solar system is made up of our sun. So 99.8% of the mass in our solar system is plasma. So yeah, that makes up most of the stuff in our solar system, in our universe. Different properties of matter. These are words that we don't use a lot in the course, but you still will need to use them. We have extensive properties and intensive properties. An extensive property depends on the amount of matter that is present. For example, if you had something like volume, right? What's the volume of this water? Well, it depends on how much water you have. If I have just a few molecules of water versus a bucket of water, the amount of water there is going to affect the volume of water. The mass, you can bet that picking up one small bottle of water is a lot different than picking up that bucket. It just depends on how much water is in there. Or energy content, like calories. Okay, something like a piece of ground beef or a piece of chicken, the energy content, the number of calories in that thing are going to depend on how much of that ground beef or how much of that chicken is there. If we're going to go the other way with it, we can think about intensive properties by looking at melting point. It does not matter how much water I have, whether I have that bottle of water or the bucket of water. The melting point of water is still 0 degrees Celsius. It does not matter how much of the water I have. It's still 0 degrees Celsius. Similarly, it does not matter how much water I have. That water is still going to boil at 100 degrees Celsius. Now, again, I'm not talking about energy content. Don't let this mind flub fool you. When you boil water, if you have a lot of water, it affects when that thing is going to boil. That's different than saying the boiling point has changed. What you're experiencing there is it takes a lot more energy, right? That's why you have to leave it on the stove longer. It takes a lot more energy to raise the temperature of a larger amount of water to the boiling point, but the boiling point is still the same. And then density. The density of a particular substance is always the same. It does not matter how much of it you have. When we look at separating mixtures, we have something like this weird looking sandy stuff. There are ways that we can separate out this heterogeneous mixture here. We can separate this out, but how are we going to do it? When we look at something like this, we have all these dyes, and we have this, there's a chromatography paper. The components of dyes, such as ink, may be separated through paper chromatography, okay, which is something if we can get some chromatography paper will try that. We can separate things by distillation. Okay, if you've seen things on bottles like 3 times distilled or something like that, this is the process of distillation. And distillation works because different substances within this substance vaporize, or they turn into gas at different temperatures. Now, distillation, most commonly is going to be trying to isolate alcohols out of a liquid. So if I have some sort of sugary water here, and I throw in some yeast and they metabolize it and they put out all this alcohol, I'm still going to have a certain amount of sugary water here. But I want to get rid of the sugary water and only have the alcohols as the distillate. And so what I'm going to do is I'm going to very carefully maintain a temperature using this Bunsen burner or a hot plate, and I am going to only make it hot enough so that the alcohols will vaporize, but the water won't. I do not want the water to vaporize, so I'm going to need my temperature to be somewhere around 75 to 80 degrees Celsius. If it bumps up to 100 degrees Celsius, well, now the water is going to start vaporizing and rising up and then condensing into this flask over here. You can also separate a compound using chemical means. One way that we do that, we can apply electricity. Okay, and water can be separated into its elements. For example, we have oxygen gas. We're going to make oxygen gas. We're going to make hydrogen gas. We take some water, obviously made of hydrogen and oxygen, and we're going to hook it to a battery. Okay, the flow of this electric current is going to force the lysis, the lysing, right here on this part of the word. The electricity is going to cause the lysing of the hydrogen and oxygen. It's going to split the oxygen and hydrogen apart. So you're going to have oxygen and hydrogen separate individually. I'm going to split reactants and products. And then there you go, representing word equation, balanced chemical equation. Hooray! All right, guys, that is going to do it for Chapter 1. Please make sure that you have attempted the problems associated with Chapter 1. Make sure that you have attempted to annotate your entire chapter of notes and that you've attempted the sample problems in those notes. If you're having difficulty compartmentalizing the different portions of this chapter, don't hesitate to simply look at the sections like the 1.2, 1.3, 1.4. Don't hesitate to use your review notes. And if that's still not helping you, contact me. You have my contact information. Contact a fellow classmate so that you guys don't get behind this early in the course.